All right, so solving logarithmic equations. So A, we're going to solve the log base 3 of x is equal to 2. So starting with very basic logarithms. In order to solve this log, there's two methods. One method is to rewrite it as its equivalent exponential, and the other one is to exponentiate both sides or use the inverse operation to the log base 3. So we'll do the way that's most common first. I'm going to rewrite it as an exponential equation. So exponential base 3 power 2 is going to be equal to the argument 3 squared is equal to x. So that means 9 is equal to x. Now, I do prefer to think about it in this fashion instead, even though it takes a little longer. So I tend to solve it this way, but knowing that it's true because of this reason. So what we can do is we can use the inverse to the log base 3. So the inverse to a logarithm is an exponential, so I can exponentiate both sides of these equations by 3, which means that these will become the exponents. So 3 to the log base 3 of x is equal to 3 squared. Exponential base 3 and log base 3 are inverses, so we'll get x back is equal to 3 squared, which is 9. So we get exactly the same answer. This just takes a little more writing, which is why we tend to do it in this way as opposed to this way. But this is true because of this. So if I want to solve this, I'm going to rewrite it as an exponential. So 2 to the 0 power is equal to 5x minus 4. 2 to the 0 is equal to the argument. And 2 to the 0 is 1 is equal to 5x minus 4. So adding 4 and then dividing by 5, we get x is equal to 1. Now, we really are supposed to check logarithmic equations because they're not always, there's not always a solution. If the argument is 0 or less, this is going to be undefined. So we have to verify that the arguments are greater than 0. So plugging in 1, 5 times 1 is 5, minus 4 is going to be 1. So this argument would be 1. And the log base 2 of 1 is equal to 0. And the same thing here. This argument is greater than 0 because the argument is going to be 9 when you plug it in. So we just have to double check. That the solution does work. Natural log of x minus 1 minus 7 is equal to 0. So in order to solve this, we have to isolate the logarithm, which means I'm going to have to add 7 first and divide by 5 second. So natural log of x minus 1 is equal to 7. And then divided by that 5, I'm going to have natural log of x minus 1 is equal to 7/5. Now remember that natural log is the same thing as the log base e of x minus 1. And we're going to rewrite it as its equivalent exponential equation. So e to the 7/5 is equal to x minus 1. And isolated x by adding 1. E to the 7/5 plus 1 is equal to x. Now if you want its decimal approximation, we can plug that 7/5 into the e function. So it's in the same spot as your natural log button. If you hit second natural log, you'll get e, 7 divided by 5, and then add 1. We get about 5.0551. So I'm going to say about 5.06. Now we're going to double check that the argument is still positive. So if I plug in 5.06 into here, 5.06 minus 1 is going to be 4.06. So this argument is still positive, which means that this is the solution. So if I want to solve that, what I have is the left-hand side is 2 logarithms. So there's no way to rewrite this as an exponential when I have two logarithmic terms on the left-hand side. So I'm going to condense the logarithms using the properties, and I know that the addition of the logarithms is, and multiplying those, I get x squared plus 6x is equal to 3. Now, rewriting it as an exponential equation, we have base 3 raised to the third power is equal to x squared plus 6x, which is 27, is equal to x squared plus 6x. I can't isolate x as it sits because this is a quadratic equation, which means the way we solve it is we set it equal to 0. Now you can use a quadratic equation or factor. In this case, this factors to x minus x plus 9 times x minus 6. So I get solutions or possible solutions of -9 and +6. Now, remember that we're allowed to have negative answers. We just have to make sure that the argument is still going to be positive. So if you plug in -6, well, this is going to be the log base 3 of -9. That means that this argument is going to be negative. The same thing here. So this -9 is not a solution because I have negative arguments. But if you plug in 6, it'll work for both here and here. Those will both be positive. This will be a +6. This will be a +12. Therefore, that is going to be a solution. But if you have logarithms inside of logarithms, a logarithm composed with a logarithm, the way we write this is we have to handle the outermost logarithm first and the innermost logarithm next. So I'm going to rewrite it as an exponential. So 2 raised to the first power is going to be equal to the log base 3 of x. That 2 to the first is going to be equal to its argument. Or 2 is going to be equal to the log base 3 of x. Now what I need to do is I need to rewrite this as its equivalent exponential. So 3 squared is going to be equal to its argument, which is x. So that means x is equal to 9. This is different because what I have is I have a logarithm on both sides of the equation. So it's already a single logarithm is equal to a single logarithm. So one way we can do this is we can exponentiate both sides by 7, or you could rewrite it as its exponentialist form as well. So if I rewrite this as if I exponentiate both sides by 7, that's going to be 7 to this exponent, 7 to this exponent, and you can see that the 7 and log base 7s are going to cancel, so I'm just going to get the arguments back. Or if you want to rewrite this as its equivalent exponential, we'd say 7 raised to this power is going to be equal to this argument, which is 2x minus 5. And we can see that 7 raised to the log base 7x plus 3 can just be x plus 3 is equal to 2x minus 5. Now, most of the time that doesn't need to be shown. If I have a log base 7 on this side and a log base 7 on the other, then the arguments have to be the same. So the arguments have to be the same, which is usually the way we pull that off. We just say if they both have a logarithms have to be equal. So 2x minus 5 has to be equal to x plus 3. Now we can solve for x. So subtracting and then adding 8. Now we have to double check that the arguments are positive. So 16 minus 5, that's a positive number. 8 plus 3, that's a positive number. So that means arguments are positive. That means this is a solution. So let's complicate it just slightly. Same exact kind of idea. Log base 4 of x plus 1 plus log base 4 of x minus 4 is equal to log base 4 6x plus 12 minus log base 4 of x plus 2. So we're going to condense both of these logarithms. So addition becomes multiplication. So this is going to be the log base 4 of their products. So x plus 1 times x minus 4. And I can do that multiplication. So log base 4 of x squared minus 3x minus 4. And over here we have subtraction. So this is going to be the logarithm of their quotient. So this is 6x plus 12 all over x plus 2. And if you notice that 6x plus 12, they have a common factor of 6. So this is x plus 2 all over x plus 2, which means this is just going to be a log base 4 of 6. Now, if their logs are the same on both sides, this both has a log base 4, that means their arguments have to be the same. So I have x squared minus 3x minus 4 is equal to 6. And the way we solve quadratics is isolated instead of equal to 0. So x squared minus 3x minus 10 is equal to 0. And this will factor to x minus 5 times x plus 2 is equal to 0. So I get x is equal to 5 and x is equal to negative 2. And then we have to double check to see if the arguments are positive. So 5 works here, 5 works here, works here, and works here. So 5 is a solution. Negative 2 doesn't work for this one. This will be an argument of negative 1. So that means that is not a solution. So 5 is our only solution. Now our last, so what happens if I have a logarithm that is composed with a quadratic equation? So solve log base 2 of x squared minus 6 times the log base 2 of x plus 8 is equal to 0. So this is quadratic form because we can write this as u squared minus 6u plus 8 is equal to 0, where u is going to be equal to that log base 2 of x. You can see that u squared minus 6u plus 8. We usually do a u substitution because it's easier to look at a quadratic in this form as opposed to this form. But we know this thing factors. This is going to be what? U minus 2 times u minus 4 is equal to 0. So I get u is equal to 2, and I also get u is equal to 4. Now remember, the original equation is asking you to solve for x, not for u. So what we're going to do is we're going to reintroduce our log base 2 of x is equal to 2, and log base 2 of x is equal to 4. And then I can solve these two logarithmic equations by rewriting them as exponentials. So x is equal to 4, and then 2 to the 4th is equal to x. So x is 16. And those arguments are both positive when I plug them in. So these are both solutions.